Okay, we're back. So in the previous video, in my opinion, the important take-home message from that video was, notice that if I have a wire carrying current flowing into the page, the magnetic field created by that wire is going to wrap around that wire in a clockwise direction. That's B. Now, separately, I can choose to walk around that wire. Each step I take around that wire, I think as a vector delta L. The step has a certain step length. That's like the magnitude of my step. And the step has a certain direction. Around here, I'm walking up. Over here, I'm walking to the left. Here, I'm walking down, and so on. Now, if the magnetic field wraps around the wire in a clockwise direction and the path I take, which is just the sum of many steps, wraps around the wire in a clockwise direction also, then this term, strength of the magnetic field, the size of my step, the angle, cosine of the angle between one step and the magnetic field at a single point. If I make this calculation and add up the contribution over every step around the entire closed loop, I don't know what number that is going to be, but I can be guaranteed this number will be something greater than 0. Because here I have if I have two vectors that are both pointing to the right, here and here, well, I'll have a certain number for the strength of the magnetic field. I'll have a certain number for the size of my step. And the cosine of this angle is going to be, well, up here, this angle is going to be pretty close to 0. Even over here, the angle between the step and the direction of the magnetic field is going to be something between 0 and 90. So my cosine will be, I don't know, let's say cosine of 20 degrees. Cosine of 20 degrees is still a positive number. And you could convince yourself that as long as the path you take is in the same direction as a magnetic field, whether it is clockwise or counterclockwise around the wire, then this summation will always be positive if that's the case. So what is this going to be actually equal to? What are we going to do with it? To think about what we're going to do with it, let's think about what this might be. So I don't know what B is, but I know the strength of the magnetic field depends on how far away you are from the wire, and it also depends on how much current is flowing in the wire. We have B equals mu naught I over 2 pi r. So if we have a current flowing, over here we're pretty close to the wire. That means we'll have a big magnetic field. Out here we'll have a small magnetic field because we're kind of far away from the wire. But B is always going to be a number. It's going to be something. And you could convince yourself that if we crank up the current flowing through the wire, well, that will make the magnetic field bigger everywhere here. And if the magnetic field is bigger, that will tend to increase the size of this term in every step of the summation. So, in my opinion, Ampere's law has a lot of similarity to the style of thinking when we think about Gauss's law. So here's a picture of Gauss's law for electric fields. And let's not worry about equations. Let's just think about what Gauss's law says. If I have a closed surface, so here are two closed surfaces. If I have a net charge inside that surface, I will have more electric field lines exiting the surface than entering because I have a positive charge. That electric field is going to exit the surface. In this case, I have no net charge inside the surface, so whatever electric field line enters the surface must also exit the surface. Now, Ampere's law is kind of a very similar creature. If I am walking in the same direction as the magnetic field, I will walk around some amount of current. And if I walk around a current of 1 amp, I'll have some value for this term. If I walk around a current of 2 amps, let's pretend we have 2 amps of current flowing through this wire instead of 1 amp, Well, you know B is going to be larger, so every term here will be larger. So much the same way that Gauss's law connects the flux passing through a surface to the charge inside the surface, Ampere's law connects the magnetic field around my closed loop to the current that my loop walks around. And this is Ampere's law. So Ampere's law, if I have B parallel times the step length around a closed loop and I add up every step length in general, I could set that equal to mu naught times I enclosed, where I enclosed is the current that is enclosed around my path. So Ampere's law, for this equation to have meaning, it does require a closed loop. You have to come back to your starting point. And I enclosed, as I said, is the total current encircled by my loop that we travel around. So, for example, here are 3 wires. All 3 wires are flowing into the page. This wire carries a current of 2 amp flowing into the page. This wire carries a current of 4 amp flowing into the page. This wire carries a current of 7 amp flowing into the page. Well, I enclosed is the total current encircled by my loop. So it doesn't ask where the wires are. Are they all near the center? Are they spread out? It doesn't ask about the shape of the wire. All I enclosed asks about is how much current am I walking around? If you think about it, this is kind of a similar question to Gauss's law. It doesn't ask about the shape of your surface. It doesn't ask if you have one charge or many charge. Gauss's law only asks how much charge total is inside your surface. Here, Ampere's law only asks how much current is inside your surface. So here we have 2 plus 4 plus 7, 6 and 7. That's 13 amps of current is inside the surface. So B parallel delta L will be kind of weird to calculate because we have 3 currents and our path is weird. Calculating this side of the equality would be kind of a mess because, we're adding vectors and have all kinds of weird trig angles to deal with. But mu naught I enclosed, the right side of this equation, is really simple for calculating around this path. We enclose 13 amps of current, so mu naught times 13 amps will give me some number. So mu naught times I enclosed would be 4 pi times 10 to the negative 7, that's mu naught. 247, that's 13. So we get this many Tesla meter. Mu naught, if I look at this side, B is measured in Tesla, L is measured in meter, so I get Tesla meter. Now you could ask, what if we have some current flowing in and other current flowing out of the page? Well, some of these currents will have a positive sign, other currents here will have a negative sign. So in this case, mu naught I enclosed would be 2 plus 4 plus 4 minus 3 minus 5. So 2, 4, 4 gives me 10, minus 8, that gives me 2. So mu naught times I enclosed will be 2.51 times 10 to the negative 6 Tesla meters. So the rule of thumb is if you have more than one wire that you are walking around, if currents are in the same direction, you add the currents. If currents are in the opposite direction, you subtract, or take the difference is another way of saying subtract. Now, you might be wondering, why did I add the 2, 4, 4? Why did I subtract the 3 and a 5? Can we have done the other thing? For the sign convention, I am going to choose, if the path I walk is clockwise, currents that create clockwise currents, I'll call positive. If the path I walk is clockwise, then currents that create clockwise magnetic fields are positive. Currents that create counterclockwise magnetic fields are negative. So what that means is currents flowing in, I notice my path is clockwise here. This current, the 2 amp, will create a clockwise magnetic field, so I call this plus 2. 3 amp, well, if I use the right-hand rule, I stick my thumb coming out of the computer screen, my 4 fingers will wrap counterclockwise. So the magnetic field created by the 3 amp current is going to be opposite the direction of my path, so I will say this is a negative current. And then the 4 amp creates a clockwise magnetic field, the 4 amp creates a clockwise magnetic field, the 5 amp creates a counterclockwise magnetic field. So if the magnetic field is in the same direction as my path, I add them. If the magnetic field is in the opposite direction of my path, I subtract them. So up to this point, I have said that we're just considering an arbitrary path. And this path is technically, I will say, more clockwise than counterclockwise. But when we actually do a calculation with Ampere's law, we're going to want to choose a better path because this path is going to be a mess. The right side of Ampere's law is fairly easy to calculate. Just give me I enclosed and okay, I'm great. But I have a whole lot of steps, and the angle between the direction of my step and the direction of my magnetic field is changing. This is going to be a mess to calculate. Also, the magnetic field will be stronger if I'm close to the current and weaker if I'm farther away. The left side of Ampere's law is going to be a mess to calculate. So it is true that Ampere's law holds for any closed path, but not all closed paths are nice to work with. So some very convenient closed paths will have the property that the step I take will always be perfectly parallel to the magnetic field or perpendicular to the magnetic field. So we'll never have to worry about angles or weird stuff like this. This is not required, but this makes my life a lot more convenient when I'm actually trying to do a calculation. So as an example, instead of an arbitrary path around a wire, let's travel in a circular path around a wire, and let's see what happens there. So I'll get rid of the arbitrary path, and I will replace it with my circular path. And notice that every step along the way, every step I take is always going to be parallel with the direction of the magnetic field. Now, when I made the PowerPoint slide for this picture, I would have liked to have had my step arrows be perfectly lined up. It didn't quite come out perfect, but you could imagine maybe you have 1,000 steps around this path. So every step around this circular path will be perfectly parallel with the magnetic field at each of the location of those steps. So we're going to have a scenario kind of like this at every point along the way. So what are we going to do with that? Well, in the limit where this, so I'm going to just stop the video here because I'm getting close, and I will begin with another video soon.